Welcome to my class. Today's topic is soil erodibility indices. Basically, if we have to calculate the amount of soil taking place, amount of soil loss at a particular place, this is equal to uh, erosivity multiplied by erodibility. So, this will be a function of, we generally denote this as K and this as R. So, this is basically the basic universal soil loss equation. We will study the universal soil loss equation in our next topics, but the basic is that soil loss basically is the product of the erosive forces, erosion causing forces, and the soil properties of the soil which is getting getting eroded, and that is called erodibility and erosivity. So, the factors, that means erosivity factor, erodibility factor, multiply the two, that will give us amount of soil loss. So, it could be in tons per hectare. So, if I have to find out the erodibility, that means the ease with which the soil gets eroded. So, if I have to define this erodibility, so erodibility is the ease with which soil gets eroded, or you can also say the resistance of the soil towards detachment by erosive forces. If the resistance is more, erodibility will be less. Similarly, if the soil gets easily detached, easily eroded, then its erodibility will be higher. If it is not easily eroded, its erodibility will be erodibility will be lower. So, if we have to find out the erodibility of a particular soil, because in one of our topics we have already discussed what are the factors what are the parameters of the soil which determine the erodibility of the soil, and so in this case now if you have to calculate the erodibility of the soil, whether your soil is erodible, less erodible, moderately erodible or more erodible, then you have to have with you the amount of soil loss sorry. So, we have to know the amount of soil loss divided by R. So, now erodibility we have a new definition of erodibility. What is erodibility now? Amount of soil loss per unit value of erosivity. So, it is amount of soil loss per unit value of erosivity. So, I hope the things are clear to you as far as erosivity and erodibility is concerned. Let me again explain this with the help of an example. Supposing this is soil A and this is your soil B. So, here these two you have a rainstorm over here. So, this is rainstorm A, and here this is rainstorm B. This rainstorm B now this rainstorm B is falling on both these soils A and B. So, when you have rainstorm A, soil loss at A So, here soil loss at A is say 12 tons per hectare and soil loss at B is 20 tons per hectare. Now, you have rainstorm A, same rainstorm falling on two different soils leading to different soil erosion rates. This is what we call as soil erodibility. So, this is because of soil erodibility. That means, soil B is more erodible than soil A. On the other hand, if you have say soil A and rainstorm A and then rainstorm B. So, on this soil it is causing 20 tons per hectare and it is causing 30 tons per hectare. So, same soil, but two different rainstorms causing different erosion rates. This is the erosive value of the rainstorm or what we call as erosivity. So, this is your erosivity. So, I hope now the difference between erodibility and erosivity is clear and generally this K value, if it is less than 0.2, we call this soil as less erodible or more resistant, less erodible. If it is between 0.2 and 0.3, we call this as moderately erodible, and if it is more than 0.3, we call this as highly erodible. This is generally the thumb rule, that how we classify the erodibility of the soil. Now, the question is, if you are asked to find out erodibility of the soil, you need to have two parameters. One is amount of soil loss. So, if you are asked to find out the amount of soil loss, so that means you will have to wait for the rain to occur. Then rainfall is not in your control, at what intensity, how to measure the runoff and all that. Even if you are going for simulated rainfall conditions, even then you have to apply the rainfall over a certain plot size, then collect the runoff in a container and then measure that runoff, then try to separate that sediments and find out the amount of soil loss which has taken place, then divide it by erosivity of that rainstorm. So, erosivity calculation is okay, kinetic energy you can find out, but this process is very tedious to find out the amount of soil loss, and you will have to do this for every type of soil you have for which you want to go for studies, and every time you have to do it. In order to avoid that, we instead of calculating actually measuring the erodibility of different soils, we exploit the properties of the soil to frame certain erodibility indices. So, that if based on certain property you say okay, based on this is the erodibility of that particular soil, you can have an idea and you can then design your various soil and water conservation measures accordingly. Because if you are asked to go for soil conservation measures to control the floods or something like that, you need to know the erosivity as well as erodibility of the soil. So, this is very important because some soils are less erodible. You need not to worry that okay, if this rainstorms come over, I should not worry, because whatever soil erosion will take place, it will be within tolerable limits, soil loss tolerance what you call as. So, what are those indices? We will now study one by one, based on which you can have an idea about the soil erosion taking place. So, again the rubbing issues, but anyhow I will manage it. The most difficult measurement in soil studies is measuring the runoff and soil loss, very tedious process. You have to simulate the rainfall, and simulation is not an easy task. You have to standardize your this rainfall simulator, so that whatever rain you are simulating, it should resemble the natural rain which you have in your particular area. So, most tedious process, that is why we avoid the actual measurement of the soil erosion. So, based on that soil properties, we then define erodibility. So, the first index is dispersion ratio. What is dispersion ratio? It is the ratio of percent silt plus clay in undispersed soil to percent silt plus clay in dispersed soil. Now, here give me a couple of minutes to explain what is dispersion. If you remember while going for particle size analysis, you have two steps. First, dispersion of the particles, soil aggregates, they get, you have to disperse those, and dispersion means converting the aggregates into primary particles. You have to remove the cementing agents by different procedure well. So, once your particles, sand, silt and clay, they are there in the suspension, then you use sedimentation method and you separate clay and then silt and sand, and ultimately find out the percentage of each. Now, here in this case, you do not I mean in numerator, you do not have to disperse the soil. You simply put the soil in water, shake it say for 2 minutes, 3 minutes or even 5 minutes, end to end shaking, and then measure you take out a sample as you do in case of mechanical analysis or particle size distribution analysis. You take a 50 ml sample, transform into beaker, dry it in the oven and see what is the amount of silt plus clay. Either you can use international pipette method or you can use that Day's hydrometer method. Then this denominator, this is exactly what you do in case of particle size analysis exercise. You have to disperse the soil and then find out the percent of silt and clay. So, this ratio of the two, this gives us an idea that how easily silt and clay get into suspension during rainfall. Because when rain falls, if water is there, and if your soil is more erodible, its silt and clay particles will get easily dispersed, and you can measure that what is the proportion of, and those dispersed particles will give basically the numerator, and then denominator you already have. So, taking the ratio of the two, you get an idea about the erodibility index. So, here the disadvantage is that it is not taking into consideration, it is giving undue importance to silt and clay particles. So, how they disperse, but the question is when rain falls, then it detaches some particle. It is not simply, but on the other hand, when you are measuring these particles, you are simply doing it, putting it in water and shaking, end to end shaking, and then find out silt and clay, which does not actually simulate the actual field conditions. So, anyhow, but still it is used widely. Second index is clay ratio. So, this is basically the ratio of sand plus clay, silt percentage, percent sand plus percent silt divided by percent clay. So, here if the clay is more, this erodibility clay ratio will be less. If denominator is higher, value will be less. If this is lower, so it is basically because clay itself acts as a binding agent. It binds the particles, it makes the aggregate stronger. Stronger aggregate is less erodible. It does not get broken down easily by the falling raindrops. So, here this parameter clay ratio, it gives more importance to clay particles than anything else. So, here it stresses the importance of clay. Then third is what you call as erosion ratio. Erosion ratio, this is basically a combination of the two. You can say it is the ratio of dispersion ratio to the ratio of clay and moisture equivalent, that is percent clay divided by moisture equivalent, and then moisture equivalent is basically nothing but 1/2 of water holding capacity. So, now beauty of this index is that it is taking into consideration how easily the silt and clay particles they get dispersed. Number 1, it gives importance to clay and it also gives importance to water holding capacity of the aggregates. So, 3 parameters these are basically combined. So, ease of dispersion, then silt dispersion of silt and clay, then clay itself as a binding agent, and then water holding capacity of the aggregates. So, that is why this looks to be better than these two, it incorporates more parameters. Next is surface aggregation ratio. What you call as SAR. So, this is the ratio of surface area of particles, greater than 0.05 millimeter to percent silt plus clay in dispersed suspension minus percent silt plus clay in undispersed suspension. So, here again it gives an idea due importance to soil aggregation, because this dispersed minus undispersed, this if this difference is less, then it means the soil is well aggregated, the aggregates are stable, erodibility will be less, and then surface area of the particles. So, smaller the particles, I mean more is the surface area, more will be the erodibility. Then last is erosion index. Basically, all these indices which we have discussed, there are many more indices, these are most commonly used. Many of these indices basically are based on the soil properties, not simulating exactly what happens in underground situation. Then to avoid this or to take care of this, Ratan Lal, while working in Nigeria, he gave an index called erosion index. So, but he tried to simulate the actual field conditions. How? That we will discuss just now. So, what he did was, so this is erosion index EI. So, what he did was, he simulated a raindrop. Raindrop simulated under lab conditions, falling from a height of 1 meter. And then this drop, it fell on an aggregate. This is your this is soil aggregate. Now, the drops, single drop, this I should say it is single raindrop. So, single raindrop technique, through this technique the raindrops remained falling on this aggregate till this aggregate was completely dispersed. So, simulated raindrops till aggregate was completely dispersed. And the number of raindrops to disperse the aggregate was recorded. So, say number is 1, and he said that erosion index is then inverse of this number of raindrops 1 over n. So, this is how he gave an index. This was developed by Dr. Ratan Lal, and he did this in Nigeria. Then our group at Punjab Agriculture University, Ludhiana, we further modified this group. What we did is that we also counted the number of raindrops. Then we calculated the kinetic energy of all the raindrops. And say this number is n. So, in our case we said for complete dispersion EI is equal to the kinetic energy of these raindrops. We had their terminal velocity, because this raindrop, it was a standard D50 raindrop, because we calculated the standard size of, you can say D50 of our rains what we have over in Punjab, and then we calculated the D50, then we simulated that size, particular size of raindrop, that was D50 size, and then recorded the number of raindrops to completely break down the aggregate, and then calculated knowing the velocity. Mass was known to us because raindrop size and mass, these are directly related, and then we try to find out kinetic energy. So, we said that this is the kinetic energy which is used to break down this aggregate. Higher the kinetic energy, lesser is erodibility, and vice versa. So, this is how these drops, raindrops, these erodibility indices are being used by different people working over there. And yes, many more indices are there, but these are most commonly used indices. And last one, I should say, it to some extent, not exactly, to some extent, it simulates actually what happens in the ground, because at the ground level it is the kinetic energy which is being used to break down the aggregates for detachment of the soil, and then the runoff which carries the detached soil particles. So, particles we carried only if the bigger aggregates, those are broken down into smaller ones or into primary particles, and then these are carried away or transported by the running water. So, I hope this is clear, erodibility indices. Thank you very much for today. So, we will meet next time. Thank you.